2 weeks ago, I went to the Perimeter Institute in Canada for a conference, and here I'm going to present the poster that I presented, which is about these ensemble spaces that we are developing, and then I'll go through some of the things that I figured out, ideas that I had while talking to other people there. So this is the poster. It's again about this idea of generalized ensemble spaces. We're basically creating a theory for states and processes for all physical theories. We want to start with the idea that physical laws need to be testable, and they have to be testable in a repeated way, and therefore the main object that we need to have, at least one of the important objects that a theory, physical theory needs to have to be testable, is the idea of an ensemble, because what we produce in labs are ensembles, and what we measure are ensembles. So we always prepare statistical reproducible copies of some preparations, and then we go and get measurement in a statistical way. So we prepare ensembles and we measure ensembles, and therefore one of the core things that we have to have are ensembles. And so the first order of business is to identify those premises that all ensembles must have to be able to be called ensembles. So that gives us the minimal requirements that a physical theory must have. Okay, so we have three essentially groups of axioms that we're going to have. The first set of axioms is is the idea of the axiom of ensemble that tells us that the samples exist and they have to be distinguishable experimentally, meaning that they have to be, we must have enough experimentally verifiable statement to be able to identify the elements of an ensemble, tell ensembles apart. And this, as we already know from previous work, this gives us a topological structure where the verifiable statement correspond to open sets, and the possibilities, so the possible things that can happen are the points of the space, and theoretical statements, statements that are associated with experimental tests regardless of terminations. These correspond to Bernal set. And I'm not going to talk about this in detail because we already have other videos about it at the summer school and so on. So anyway, so that's basically the idea. First set of first set of axioms tells us we have ensembles that are experimentally defined, therefore they are points of a T0 second countable topological space. Then the second set of axioms that we're going to have regard mixture. So something that we always need to be able to do with ensembles is a statistical mixture, meaning that we have two preparations that prepare two type ensembles every time, and we can put a selector such that 30% of the time we select one ensemble and 70% of the time we select the other ensemble. So this now becomes a different preparation, that it's a mixture of the two. And this mathematically is captured by the idea of a convex combination. So it's a combination of elements where you're summing them and all the coefficients are between 0 and 1 and they all sum to 1. So A and B and all the elements between A and B, the line between A and B, correspond to all the possible convex combinations. It's a linear combination. Linear combination will go extend outside A and B, but if we're making a convex combination, you can only be inside. So that's it. And this is again something that we must have. And the other thing that ensemble must define is the notion of an entropy. And this because the idea is that the ensemble must be some sort of definable in some sort of equilibrium, in the sense that it's always defined, always equal to itself. And it's going to be made of different elements, and the entropy is essentially a measure of the variability of the elements within the ensemble. And so the entropy is a function of an ensemble that gives us a real number. So for every ensemble, we get a real number, which is the entropy. And the entropy is going to be strictly concave, meaning that if we make a convex combination of ensembles, the entropy of a convex combination must be greater or equal to the average entropy of the elements before. And it's equal if and only if all the ensembles that we're combining are exactly the same. So the entropy, essentially, when you're mixing different things, the entropy always has to go up. And then we have an upper bound on the entropy, which is given by the Shannon entropy, meaning that if we are taking two things that are completely different, then in that case the entropy increases by the choice of selecting one or the other ensemble. And this gives us an upper bound to the entropy that actually corresponds to orthogonality both in classical mechanics and quantum mechanics. Two ensembles that saturate this upper bound are orthogonal in classical mechanics, meaning that they are in different subspaces, and in quantum mechanics well, in classical mechanics means that the distribution has different support, while in quantum mechanics that they are live into orthogonal subspaces. And this idea of orthogonality gives us already a difference between classical mechanics and quantum mechanics. In fact, it gives us a way to fully characterize classical spaces, because so from the convex structure, we can define two elements as not having a common component. There is E1 and E2 here in the examples do not have a common component if there is no E that summed with something else gives us the two ensembles. So for example, there in the picture, we have two distributions, and since these two classical distributions do not have an overlap, then there is no sub-ensemble that we can sum to get both distributions. So in classical mechanics, if two things do not have a common component, it means that they have two different support, and of course the space of the distribution on different supports form orthogonal subspaces, because if you now take the two distribution and multiply to each other, you get a zero everywhere, and then therefore the norm of that is going to be zero. So not having a common component means being orthogonal in classical mechanics, but not in quantum mechanics. For example, here we have the block sphere here in the picture on the right, and here in the picture on the right, and what happens is that when we consider A and C are two pure states, and the two pure states lead at the boundary, and they don't have components. We can't find the sub-ensembles of pure states. They are extreme points in the convex set, and so A and C do not have a common component, but they're not orthogonal, meaning that if we take A and C and we sum them, for example, the maximum entropy that we're going to get is less than 1, so they don't increase maximally. For two ensembles to increase maximally in quantum mechanics, they have to be orthogonal. So A and B, for example, they are on opposite sides, then they are orthogonal, and the point in the middle is the point that is going to have the highest entropy, because it's the maximum state, and that means that we can increase the entropy maximally. So A and B are orthogonal, and they also do not have a common component, but A and C are not orthogonal and have a common component. So the difference between classical mechanics and quantum mechanics is this ability of creating different mixtures in actually the same mixture in the same way, and this leads in quantum mechanics the two property not having a common component and be orthogonal to be different, while in classical mechanics if two things do not have a common component, they are orthogonal. And you can go the other way. If you say I have an ensemble space and every pair of components that do not have a common components are orthogonal, then you can show that you have a classical probability space. So these are the type of things that we are still trying to sort of formalize in this framework, but things work quite well. We can already pinpoint one fundamental property of classical spaces with this characteristic. Another thing that we want to be able to do here is to build constructions that recover things in classical mechanics and quantum mechanics, but when we do this construction, we can define them regardless of what space that we have. So the constructions are exactly the same. And the idea is that that way we can sort of generalize theorems and results at the general level. We don't have to know whether we are in classical mechanics and quantum mechanics. So for example, what we want to define in this framework is something that then becomes a probability both in classical mechanics and quantum mechanics. And here's the issue that, probability doesn't work exactly in the same way in classical mechanics and quantum mechanics. So what can we use that works well? So this comes from this problem comes the idea of a fraction capacity, and it's basically a non-additive extension of probability. And the problem that we're trying to solve is this. Suppose that I give you an ensemble E and a set of ensemble A. So from A you can make a bunch of mixtures, you can make a bunch of different ensembles. And you're asking, what is the biggest fraction of E that you can express from A? So, E could be written as the sum of many things, and we want to write E as the sum of something built from A and something else that is not built from A. And we're asking what is the biggest element, the biggest fraction that can be explained from A so that we can get E. So the idea is that we can then write this for any E we can get an A, and we find the biggest P such that E can be seen as a convex combination of A. And then from A, we can get the A, the big set. We take the hull, and the hull is the set of all possible convex combination. And we find the one that has the biggest fraction capacity. And now this is, we're taking the supremum, so we find the biggest element, the biggest fraction that we can have for E as E as a convex combination of elements of A. And we take the supremum because we want to be able to essentially take a limit. That fraction P might not be something that that we can actually achieve, but it's going to be a limit, and that's what we want. And now sort of by definition, f cap is a function that is going to return a number from 0 to 1 because we're taking the supremum of a number from 0 to 1, so that's all that we can get. So it's a set function that it's non-negative. It's unit bounded because, again, 1 is the biggest that we can have. Is monotonic because if we increase A, we increase the possible convex combination, we can only get a fraction that is bigger. We are not going to be able to get a fraction that is smaller because all the previous elements are still there. And it's subadditive, meaning that if we have two sets, A and B, and we put them together, the fraction capacity of A union B is going to be at maximum the sum of the two fraction capacity. And it's going to be the sum exactly when we have orthogonal subspaces. And so this, in general, gives us a fuzzy measure. It gives us a not additive measure. And we recover additivity in classical mechanics, because in classical mechanics, everything that has no common component becomes orthogonal. So you're looking at everything decomposable in orthogonal subpieces. And also for quantum measurement, because in quantum measurement, we are going to take an orthonormal basis, and so we're going to have orthogonal subspaces, and therefore the distribution over the orthogonal subspaces is going to be additive. So the idea is really we have this general definition that only works on the on the convex structure, right? Only knows about the convex structure, and we're able to go and recover things that that are both in classical mechanics and quantum mechanics. So the idea of probability when you have the additivity. And everything that we can sort of define in general is a sort of a generalization of the count of states that we already have in classical mechanics as the Liouville measure of phase space. And here all of this is possible by this insight. By the previous definition that we have, we can show that the exponential of the entropy is subadditive when you're making convex combinations, such that 2 to the entropy of a convex combination is less or equal to the sum of 2 to the entropy of the elements. Here is missing actually a P1 and P2. I'm just noticing now. So yes, there should be a P1 and P2 here. Okay, so you have this, so this that you can note, and what you find now, what you can define is this state capacity, which is going to be again the supremum of the exponential of the entropy of all the possible convex combination of a subset A. And so we have the set A, and you're basically trying to find how many states you can fit in those distributions. And again, if you know in classical statistical mechanics, you know that the entropy of a set of phase space is, or of a uniform distribution over a set of elements in a phase space is the logarithm of the volume, right? So you have the entropy is the logarithm of the volume. So now we have the 2 to the entropy is equal to the volume. So the state capacity really recovers the volume of the state space in terms of possible states. So again, we have a set function, something that gives us a set, that from a set gives us a real number, which is non-negative because the exponential is a non-negative number. It's monotonic because if we increase the number, the set, the hull can only become bigger, and the supremum is always going to pick the biggest element, which can only increase. And again, it's subadditive because of this relationship that we have seen before. And therefore, it's a fuzzy measure. But again, across orthogonal subspaces, you will find that you're going to have an equal of this inequality, and therefore you're going to recover the classical Liouville measure, so for classical mechanics. And you have a quantum analog that it's useful to sort of get some intuition. So again, so these are two constructions that we are trying to study, and this is part of the grant that we got from the John Templeton Foundations to understand better the use of non-additive measure in the context of quantum mechanics, which means in this, for us, in this extended way of looking things. So everything that we can do directly from the entropy, if you remember, we had these two bounds on the entropy, a lower bound and an upper bound. And you can always see that it's the entropy of the mixture is related to the average entropy. So what you can do is define this. You can have the entropy of the equal mixture of two states minus the average entropy of the two states. And now if you look at the definition, this is going to be between 0, which is 0 when the two states are going to be exactly the same, and 1, which is when the two elements are orthogonal. And so this sort of gives you a pseudo distance. It's not a distance because it does not satisfy the triangle inequality, but it recovers Jensen-Shannon divergence both in classical mechanics and quantum mechanics. So that idea of looking how far two elements are by mixing and see how much the entropy increases, this idea is something that we can have more in general, regardless of whether we are classical mechanics or quantum mechanics. We don't even know whether we have one of the two. In fact, it can also work in general for any ensemble space. Now, another thing that you can do, and this you can do only if you have a space that is the convex space that embeds into a vector space so that you can define the notion of a tangent space. And in those cases, what you have is that since the entropy is strictly concave, if you take the Hessian, the second derivative, that Hessian is negative definite, because the second derivative must always be negative. Now, if you stick a minus sign in front of it, now it becomes a positive definite, and it's a positive definite function of two elements of essentially the tangent space in the affine structure that is defined by this convex combination. And so this now can work as a metric tensor. And this metric tensor actually is exactly the Fisher-Rao metric for classical mechanics, and the Bourret metric, the Fisher-Rao metric equivalent for quantum mechanics. So you really recover the geometrical structure of these spaces in terms of information theory without doing much work. You just do a simple definition, and again, it's something that we can work on in more general spaces. And so you say, okay, for this thing, we required something more. We required the convex structure is also a vector space structure. And this is because both classical and quantum mechanics sort of follow more definitions, have more properties than what we had in the axioms. And we have them in blue as definitions because we can't really justify these properties in general. They are valid for classical mechanics and quantum mechanics, but we believe that there might be physical spaces that might be useful that don't follow this property. And so if we following here says the above properties are satisfied by classical mechanics and quantum spaces, not obviously justifiable a priori, and so there is possible new physical theories they are lurking around, and we really think so. But for classical and quantum mechanics, one of the things that you need to get the vector space, the additional property, is this idea of a complemented space. So if we're doing mixture, we're taking two elements and we create mixtures, right? So we go from things that are better specified to things that are less specified because they have more uncertainty built into it. And now the idea is that we want to define some way to go backwards. So if we imagine that we have this linear combination E, P, E1 plus B bar E2, typically you fix E1, E2, and P, and you recover E. And now we're going to say we're going to fix E, we're going to fix P, and we're going to fix E1, and we're going to try to see if there is an E2. And if the space is complemented, if E2 exists, then it is unique. So basically, in general, in a convex structure, if we went backwards, we could find different things that mixed could give us the same result. But if we are in a complemented space, then no, we can only find one way sort of to unmix things. And in this case, that's the case where we cover a vector space. Another thing that you can define, and they're going to be useful both in classical mechanics and quantum mechanics, is the idea of statistical quantities, which are functions that for every ensemble give us a real number. So for example, position would be a statistical quantity, and for every ensemble, right, we will get an average position, an average value of the average value of the coordinate. And so the statistical quantity is not only a function of that for each ensemble give us a real number, is also a continuous linear functional. And it has to be linear because the average, the expectation is a linear operation, and it has to be continuous because f, the value of f is what we measure, and therefore, as we saw in our sort of more general theory of experimental verifiability, we know that these functions have to be continuous because the topology is really what characterized the verifiable statement, what actually can be verified in practice. Now we can, from this notion, we can define a quantifiable ensemble space. Basically, an ensemble space is where each element is identified by a set of quantities. So for example, all the polynomial position of momentum will tell us the distribution of the ensemble that we're looking at. In this case, these quantities essentially can be used as semi-norms for the topologies that generate the topology, and therefore we are going to have a locally convex topological vector space. And the locally convex topological vector space are the things that are used, the mathematical objects that are used in sort of the biggest generation of calculus, and it's nice that we can actually recover those definitions clearly by basically saying we have ensembles and we have enough quantities to identify these elements of the ensembles. And again, this works for both classical mechanics and quantum mechanics. And the other thing that is true in classical mechanics and quantum mechanics is this idea of orthogonal decomposability. So if you have an element, an ensemble that can be written as a mixture of two ensembles, then we can find two ensembles that are orthogonal to each other that when mixed recover the original ensemble. So for every ensemble, we can always decompose it in parts that are orthogonal, meaning that from an information theoretic perspective, we can say, oh, we were in this or the other, that we recover the sort of the bits of information. And we think that this should be enough to recover the idea of an inner product space, but we haven't done the full work there. We really think that that should be the case, but that's something that it's still need to be understood. So these are things that are valid for classical mechanics and quantum mechanics. They're not valid for, we think, all physical theories. And then, of course, we're still working on identifying exactly what other things could fully identify quantum mechanics and classical mechanics. And so there are still some pieces open, but these definitions are simple enough, then they're already recovering a lot of structure that we need. Another thing that we can recover, again, with this idea of orthogonality between from the entropy is the subspaces themselves. So if we have a set of ensembles, we can define now the set of all those other ensembles that when mixed with any of the other elements make the entropy go up a maximum. So we have a set of ensembles, we find all the other ensembles that are orthogonal to essentially all the elements of the set that we have. And this is essentially the orthogonal complement. And a subspace then is something for which the orthogonal complement of the orthogonal complement is equal to the original element. And you know, if you're thinking of orthogonality really as orthogonality coming from an inner product, this is exactly what you have as a property. And we are not going to use it as a property, we're going to use it as a definition to find what the subspaces is. And this is a construction that we sort of reinvented, and then we found that somebody in the 60s already had some sort of similar ideas and did a similar construction. So this recovers subspaces for both classical mechanics and quantum mechanics, which is again nice. We want to have the things in general. So this is in a nutshell what we presented at the conference. And then what I did was to talk to people to understand a couple of things that are a little bit tricky, and that sort of gave me some ideas. So let's go to the other program so that I can draw. So one of the problems that I want to be able to address in the future with ensemble spaces is that I want something that works as I said, in the same way for classical mechanics and quantum mechanics, but also for field theories. So even classical field theories and quantum field theory should talk about ensembles and have everything well defined. And so what I need to understand is what are the possible things that can go wrong and whether I will have enough information to make the things that can go wrong or not go wrong. So in the case of just particle mechanics, let's imagine classical mechanics. So you would have a variable like x, and you would have an ensemble is essentially a probability distribution over x. So this is going to be a probability density rho. right? So there's going to be probability over distance as a value. Okay, so we have these distributions, and one of the things that we uh, absolutely do not want to have is allow for distribution that are discontinuous. So we don't want to have something in a space is that something that goes zero and then suddenly goes up and then does something and then suddenly goes down. So this idea that the value can change abruptly if our variable is continuous is not something that is going to work because we are not going to start with the idea that we have the quantities. We're going to start that in general we are going to have uh, these these ensembles, and so ideally we want to recover the subspaces, the fact that we have something a distribution that are in between, right, and all the possible distribution that have the same support, that forms a subspace. And if we allow for these things, this distribution to be discontinuous, the problem is that now topologically these things are completely separate to each other, and we are not going to be able to recover which are the open sets and which one are open sets or closed sets or not open sets. So we are not going to be able to recover in general the topology of the space from the space of X, right, from the topology of the ensembles themselves. And so one of the things that we know that we need to do is, for example, when we want to define a probability of, if I want to know what is the probability of this distribution within this support, what I'm going to want to be able to say is that I find probability distribution that are inside this support, and the one that actually goes up follow this one and goes down, like this part here, is going to be a limit. It's not going to be something that it's really in the space, but we can approximate that part closer and closer. And again, one of the things that this means that I already sort of figured out is that especially in quantum mechanics, the space, the good space that we have is not going to be a Hilbert space because again, the subspaces are not going to be closed. They're not going to have all their limits inside. And this is fine. This is something that we already figured out that we do want to avoid in both classical mechanics and quantum mechanics, because we want the topology to know essentially what the correct quantities, the quantities that define the space are. So just to give you an example, in quantum mechanics, if you use the Hilbert space, then a space for one particle or for a billion particle, they are exactly the same Hilbert space. Mathematically, they are indistinguishable. The topology is exactly the same. But this is not true in classical mechanics. If I give you the state space of a classical particle, that would be r to the 6n, and if I give you a classical phase space of a billion particle, that would be 6 billion times n. And these two things are not topologically the same. There is no homomorphism between the two, so you can say, oh yeah, I have two different spaces. And so in quantum mechanics, instead of using the Hilbert spaces, you could use the Schwartz space, and again, the Schwartz space would be able to tell the difference, because again, the topology is defined by all the semi-norm of all the possible expectation value of all the possible position momentum, which recovers the idea of what we said before, that the space is quantifiable, so we have enough variables, statistical variables, to figure things out. Okay, so this is sort of how it works for particle mechanics, and now I have to understand what are the things that can go wrong in field theories. So now in field theories, if I have x, right, then I have the value of the field at each point. Let's call it f of x, right? And now this distribution of the field, this is not a distribution like this, right? This is actually one of the points. So all of this function is one of the point, corresponds to one of the point to which we put a probability density. And so we need to be able to put a probability density on these function spaces. And again, there are issues that we want to put the probability densities on the things that are continuous, because if they're not continuous, they're going to break the topology and so on. So one of the naive things that you would have in field theory, and the people try to do, of course, it does not work. You would like to be able to say, well, the value of the configuration of the field is basically saying the configuration of the field in some range, let's say called U, and in some range U complement, right? So the U complement is going to be all the region outside. And you would like to be able to say, or you'd think you'd be able to say, well, I tell you what's on U complement, and therefore you essentially have the product of the two spaces, right? Because every field configuration of the whole is the field configuration on two elements. And you can see that this is not quite true, because you need continuity. You need that at the points things have to stitch. And if I only tell you a configuration of U and a configuration of UC, right, I could have something that does something like this on U, and then I try to stitch it with something else in UC, and it's not stitching anymore, and therefore I don't really have a full configuration on the whole thing. So it's not true that, let's say, the field configuration of U is independent, completely independent from the configuration of UC, and therefore something needs to happen. And another thing that can happen, if you just consider the set of continuous function over U, well, something that goes to infinity, right, is still a valid field configuration over U. But of course, it's not going to be a valid configuration for any field over the whole thing, because we can't have infinities on the boundary of U. So the point is that since we are looking at continuous configuration on the field, and each point on X in front of the space corresponds to essentially an independent degree of freedom, well, when the two elements are infinitely close, they're not independent anymore, because things are continuous. So this is something that needs to be taken care of in the framework. And what is also interesting is that these type of issues are the problems that you have in quantum field theory with inequivalent. They're related to the problem that you have in quantum field theory with inequivalent representation. The fact that you have essentially two sets of observables defined on the same Hilbert space, but when you go from one sort of representation, one way to describe the states, to the other, you have a problem that the unitary transformations sort of bring things that are infinite on one side to finite on the other side, and vice versa. So that you basically have sort of pieces that are sort of don't quite matching. And this is what I've described here is basically the classical field theory analog of that. And so, of course, as I always say, before cleaning up and fixing everything in quantum field theory, first I have to do that for quantum mechanics, which we are already working on, and then I will have to do it for classical field theory, because some of the issues are exactly the same. And then hopefully, once both things are nice and clean, we get quantum field theory already nice and clean, because we have solved these orthogonal problems. So this is kind of what I was trying to talk to people to figure out. And one of the things that people do in the algebraic quantum field theory, they have this idea that they have observables that are dependent on support, but they allow this idea of cutting the support like very, to chop subspaces of quantum mechanics. And if you do that, you bump into this problem of irreducible representation. You could have things that go into infinity. You have all sorts of problems. And I think that's not going to be what happens, because if you imagine measuring something on a region of space, again, we're not going to have sharp border on the region of space. And so there are some people do that approach things in a different way. And so instead of really measuring f, right, directly in a region, what they would have something that smooths out the region, right? So you have some thing that goes, let's say, from 1 to 0, and let's say that this is the region that we are really interested in you, but you see you're going to have something that is moved down, and this, you could have something that picks up the region better, like something that does something like this, right? But it's still continuous everywhere. It's not really chopping it out. And so you could imagine now to have an algebra of observables where you have all these possible ways of smoothing things. And so you would have all the possible smoothed observer as a smoothed observable and sum them. This would some sort of form some kind of linear space in which you can decompose the pieces into smaller and smaller pieces. In the same way that we decompose the ensembles, we have some kind of convex structure on the observables themselves, and that might be the thing that we need to impose, that again we don't have right now. So that could sort of be an idea to understand essentially the smoothing as a convex structure on observables and on quantities, and see whether this allows us to sort of define things well, so that we don't break the topology, and we can recover this notion of field measurement at points as a limit of this smoothing function that sort of become delta Diracs in the limit. So this is one thing that I was thinking, and I think essentially at least we have a strategy. At least I know that there might be a way to do these things for field theory. The other thing that is interesting to me instead is understanding how these quantities are going to work for theories that work at, say, a Planck scale. Because one of the things for previous work that we saw is that most likely it's very unlikely that that the assumptions that you need to have real valued quantities are going to hold at Planck scale. So the problem is, what is it going to be there if not that? Well, as you remember, we had this idea of complemented spaces, this idea that we can do sort of unmixing and find where we came from the mixture. And once you have this, as we saw, you basically have a vector space structure. So you have a vector space of the real. And once you have the vector space of a real, you can imagine that any path is going to be parameterized by a real, and so time is going to be a real quantity, and so on. So very likely if we want to say, oh, we don't want really time, space, and all physical quantities to be real numbers, very likely we are going to have to abandon complemented spaces. Okay, fine. And what is going to happen if we don't have these complemented spaces, and how can we recover the complemented spaces in the limit? Because at the end of the day, we want to be able to say that at large scale, things look either classical or quantum, so we have a complemented space, so we are going to have real numbers. So how can that work? And something, when I was talking to other people, one of the things that I realized, we're already saying that if we get quantum mechanics and we look at the entropy, high entropy limit, we get classical mechanics, so that the mixtures of classical and quantum states become more and more classical looking if we go if we basically, when we mix, things become less defined, higher entropy, and those are the ones that that actually look more and more classical. And another thing that we know both in classical mechanics and quantum mechanics, we get the thermodynamic limit by essentially taking ensembles with a large number of particles. So if we can imagine to have thermodynamics here, we can actually go either from classical mechanics and quantum mechanics for the limit of large n, which again you can imagine this being instances of ensembles where the number of particles go up. Okay, so now how do we get to these spaces if we have these spaces that are not complemented with a Planck scale and so on? One of the things that I realized, remember when I was talking to people that work in metrology, is that the way that they define time is you have a bunch of atomic clock or fountain clock around the world, and then you gather these the data from these clocks, and they're not going to be all perfectly synchronized, of course. And what you're going to do is remove the outlier, and then take the average, and now the average is your clock. And so that got me thinking, is that, okay, maybe what needs to happen is not really that we recover real numbers at large scale, but we recover real numbers at, again, higher entropy. When we start mixing things, then thing becomes more and more like the real number. So we have something that it's not complemented, right? So the idea is that we have different ways to go and then find the same mixtures, right? So if I mix this, if I fix this mixture and I say I want to mix this plus something else and obtain this, then I could be mixing this with this and this and this and this and this, and they all give me something else. So when we're mixing some things, we lose information from where we got. And so this part here is exactly the part that it's not complemented, right? And we can imagine that we could come, let's say, from different sides, right? But then the center, right, the center where the entropy is higher, this becomes looks more and more as it's complemented, because we could imagine that the differences between these ensembles become smaller and smaller and smaller, to which at some point they're basically saying, okay, we basically call those ensembles the same. And then in this part we are complemented. So in this part you have a vector space of R, and that's where you would recover classical mechanics and quantum mechanics as things where the standard math and the standard ideas would work. So that this is, of course, doesn't tell me at all how to make the construction, but it tells me a little bit what we would be looking for, right? Instead of looking something that at small scales does not look like the real numbers, but at large scale it does. What we're looking is for a set of objects. Let's call it, I don't know, Z. Let's call this set of objects Z. And these set of objects will have a convex structure, meaning that we're going to be able to make linear combinations of all the elements of Z, right? And what would needs to happen is that in this convex structure, the more you combine things, the higher and higher. The interior part of the convex space looks more and more like a real line, essentially. So the extreme points, the set of extreme points, they are unordered. You don't know what to do. But then when you you do average of average and averages, then they become more and more like the real numbers, and that's and that's how it look like. That's how we get the thing that we get by essentially statistical averages. So this is another idea that I think it's going to be important. I don't know the detail, but I think it points us in the right direction. And then the other thing that I talked to, I found some people that had competence in the foundation of mathematics and physics. So we stayed there and talk a couple of hours, 2-3 hours on these things. And it's always nice because there's so few people that know about some of these things. They're also working on some sort of pointless topology type spaces, locales, and all the other elements that I don't quite remember. And all these spaces are very similar. I never quite understood the difference between them. And I finally was able to understand by talking to this guy that basically the spaces themselves kind of look the same, but the way that you do the morphism are different. And the morphism that we're actually interested in, turns out, are the one from topological spaces, are preserving these the countable union and the finite intersection from from the inverse relationship. So it turns out that that's the right structure. The other structure is actually not interesting. But one of the things that I had as a sort of a hunch, and I expressed to them, and they seemed to agree that it might be the case, is one of the things that essentially whether we or not we need the axiom of choice. And axiom of choice is used in mathematics when you have sets of infinite elements and you need to be able to pick things from those elements. And one of the things that I finally kind of understood is that again, it's one of those ways that it's similar to this inequivalent representation. When you have infinities, you can sort of make these infinite permutations and sort of reconfigure the infinity in such a way that it looks totally different. And so just saying I have infinitely many elements and oh, they're countable, I still haven't defined how to traverse the space and what space how that space really looks like and how should I think about it. And that's kind of the issue for me, is that it can't be like that in physics. It must be that when we're talking about infinity, the type of infinity that we have in physics are some sort of continuation of things that we do over and over and we can imagine to go on forever. And so one of the things that we assume in our spaces at a foundational level, we assume that we have this second countable topology, meaning that we have a basis that is countable. And so we have a basis B that it's countable. So it's basically a set that goes from 1 to infinity. And so it's not enough to say I have infinitely many verifiable statements, because I need to be able to go and test them. So I need to have some way to enumerate this statement. I need to have really a function that you give me a number, right? And I give you one of these elements of the set, so that you can go one after the other and say, okay, after this, test this and test this. And again, if you imagine testing and measuring things for real value, you really would say, okay, I measure this at this point with this uncertainty, and then with this uncertainty and this uncertainty. So you have a way to sort of traverse this set of tests, because you need to be able to say what is the next test when it's the next test. So it's not a problem for me to say that these infinities are not just countable infinities, but I have the enumeration. And from my understanding, and that's what they confirmed, once you have these enumerations, you might not need the axiom of choice, because the enumeration already tells you how to go through the set, so the choice is always there. Okay, you can construct a choice for this enumeration. And so there may be a chance that when all this is done, because we must have the enumeration of the tests, then we don't really need the axiom of choice. And one of these gentlemen that I talked to, there is a way essentially to construct the real numbers without the axiom of choice. They suggest me that I have a look at that. Of course, I don't know if I'm going to have the time to look at that, but if there is anybody who is interested to understand whether deeply whether these things require axiom of choice or not, and if we can do everything that we want without it, that's something that I would certainly be interested in talking more with this somebody. So that's basically it. This is what all the things that I talked about, or at least the highlights from my trip to perimeters. So I hope that you'll find those interesting. And again, if you have further questions, you can always put them in the comment section below, or write me an email. So, okay, bye, see you next time.